All right, so I'm recording this. One quick thing about Monday lecture. It turns out WebEx doesn't really properly record the meeting on Monday. So I would re-record the whole session on Monday again, uh, sometime in a few days, and then I'll upload it on YouTube channel like usual. And I surely hope that at least today's session would be recorded and saved on WebEx. If not, I'll also re-record this again. I might send out the the email saying, okay, this is the time that I'm gonna do a re-recording. So if you want to kind of do a recap, quick overview, you can join this live session. It'll be a repeat of Monday. That's pretty much it. Assignment 2 is posted. I still need to kind of like work on the starter code a little bit for you guys, but the text, the content of assignment 2 is up on Canvas. I am aware that I haven't replied to emails from any one of you since Monday. I'm going through that basically as soon as possible. This week has been a little bit hectic for my schedule, so I'll try to clear it up as soon as possible. One thing that I would request in the future, it would actually help me in terms of searching for the class email. In the subject line, can you add something like MUIC, the skill, on your subject line in the email? This allows me to basically search and making sure that I don't miss any one of your email when it gets sent, because as I said, I don't want to miss any email. Uh, so today we'll switch the topic over to our third modules, and we'll cover this thing called data representation. Let's wait maybe a couple more minutes because it's still more, I think there's still like 10 more people that haven't joined us yet. Any questions about the overview of C, anything C related, feel free to kind of wrap it up and also send me an email or just ask the question now uh, while we're waiting for more people to join in. Oh, that's a great question. So one of you asked what's the exam format? It will be coding based, but it will be a little bit more open end as compared to earlier, because I need to kind of making sure that you can do the exam, but there's no direct solution that you can kind of Google it from the internet. Uh, so it would be coding based, but then there might be question that you need to explain what you're trying to do with the program. Or there might be some conceptual question that I can ask. So partially coding for most of the case, and then there'll be a little bit of the conceptual questions to make sure that you go through some of these material. And just to do a recap again, the exam will be on June 1st. It'll be a one-day exam. It will begin at the class time on June 1st. Basically 2 p.m. The clock starts ticking. I will post the exam actually a little bit before 2. Then during 2 to 4 p.m. I will be here to answer any clarification questions, anything that you have about the exam. You can either ask on the chat or just open your microphone and ask it. And then I'll make sure that got covered. Anything after 4 p.m. on that day, you can still email me about the specifics of each of the questions. But I want to make sure that 2 hours you get the chance to read through every single question. Then everything is due the next day at 2 p.m. All right, so let's begin. Let's do a quick recap about this topic from basically last Monday, because as some of you might have realized, this is a new thing. You have not really heard about data structure. So I want to make sure I give you again some example of how this can be done. But as I said, when you have this concept of pointers, you can use it to implement things like a linked list, a tree. You can apply basically a collection of items where you need to be able to actually get the next item, right? This is the general guideline. You create a struct that consists of the actual data and a pointer to the next items. Then you can declare a pointer to the first item. Inside the first item, you then have a pointer to the next item, followed by every time you need to create, this new data, this new piece of data, you need to call malloc to actually get the space associated with that pointer allocated. As I said, we will play with this in assignment 2. You'll see about, I think 4 questions that requires you to play with malloc and data structure. If you have any questions about that, just feel free to ask me those questions. All right. So we go to this first thing that we went through last Monday, especially this thing called a linked list. A linked list is something like this. You have a pointer to this first element, right? And then the first element is also have a pointer. So this is pointer. Connects the first element to the next element, then the pointer again to the next element, and this is null. Basically, at the end of the linked list is a null item, meaning that, hey, that's the end of my linked list. These operate as almost like an array, right? You have A0, A1, A2, A3. Now you have the first item, second item, third item. Then the end of every single thing in my linked list. You can use it to store data. You can use it to keep expanding this collection of data, right, that you want to store. Then we talk about instead of using a pointer, how can you actually implement a queue using an array? In the assignment, we'll ask you to use pointer to implement a queue. In here, I can show you, hey, let's look at this queue, right? We call this array a queue by just having this head and tail, right? And then in the head and tail, you can have multiple items, multiple data, right? And then when you want to enqueue, which is putting the next item into the queue, queue is first in, first out, right? So let's say you want to put in 5 into this queue. You put in 5 here by the next item and you increment the tail. So tail is now point here. If you want to dequeue, which is get rid of the first item that comes into the queue, then you return the first item. Return whatever head is pointing, right? So now you return 1, head is then moved to 2, 1 is gone. And that's it. You can use an array to implement a queue. You can then use an array to implement this another data structure called a stack. A stack is something that looks like this, right? When you push, which means that we push something into a stack, you put a data in, let's say it's a letter A, right? You can push in letter C, push in letter M, push in letter N, right? Whenever you want to get something out of the stack, this is called a pop. When you call a pop, then instead of getting the A out, that's the Q, right? In a stack, you get the last item that got put in out. So in this case, N get pop. And then you ended up with M, C, and A. This is called first in, last out. A Q is first in, first out. Then we talk about a binary tree, where you can have a node with two pointer, right? Pointer, pointer that points to the next node, right? Which also then can point to a child. One of the constraints is that this binary tree has to have at most two children, right? The left and the right. And you can have the binary tree that is more balanced, something like this, or it can be really imbalanced where one of the branches go out really, really far, right? That's also a valid binary tree. This concept has a lot of use in computer science. It's one of the most important data structure that is commonly used in every single programming language. In C, you can use a struct to create the node, then you assign the pointer to the next node. We will actually ask you to implement a version of this binary tree on the assignment too. If you go through the assignment, you see one of the questions asks you to implement exactly a binary tree. All right, so that's it for the class on Monday. As I said, some of these data structure are important. On the exam, if I want, if I want you to implement any certain data structure, I would definitely tell you how it works. But if you're not sure exactly how it works in terms of the algorithm, in terms of the thought process of like, okay, how do I deal with this specific binary tree? Email me because I want to make sure you get a good control of the C language. If the question is not specific to C language, but it's more specific to the knowledge of data structure, I would actually look at the question and answer it so that I can make sure you can go through the exam, right? Just don't ask me what's the answer. There's no way I can tell you that. So now let's go to the next topic, data representation. By today, you probably then realize now that you have multiple languages, right? Both human languages and computer languages. And somehow, right, we can ask your friend to implement a program, to actually build a program. That program will somehow run on a computer. And as I said earlier, the computer operates by looking at the voltage value. A high voltage and a low voltage is super stupid. A computer is super stupid. We as a human need to figure out how to make sure a computer understand us and how to understand what does each piece of the data mean. So you think about it this way. Computer only deal with electrical signals, zeros or ones, right? This is binary value. Why binary format? As I said, there's a high voltage and a ground voltage, which is 0 volts. Usually, basically, when you connect to the ground, the voltage between the high voltage and ground would be like whatever you feed into the main board. Usually, that's 5 volts. This can be 1.5 volts depending on the computer. And then if you look at how they figure out which one is ones and which one is zero, if you plot, right? If you plot the voltage, this is Vmax, the supply, we call this supply voltage. The voltage that you plug into the computer. This is zero, ground, right? There will be a level called VDD, which is basically the cutoff. The cutoff of if it's higher than VDD, that's a 1. If it's lower, that's a 0. So if your data behave this way, It means that in the beginning, the data has a value 0. Then someone write to the data means that it changed to 1, and then someone overwrite the data again and it changed back to 0. This is how you can actually assign a data to a variable, right? That's how you can change the data. That's how you can operate a computer. So one thing to note in the future, even now, right? These range between Vmax and zeros get closer and closer and closer. Right now, we are looking around like 5 to 6 electrons. 5 electrons means a 1. Less than 2 electrons means a 0. There's so much you can do. So these days, there's a lot of techniques that go into how to make sure you can read the correct value, both on the computer systems, operating systems, because as one of you realize, right, these days blue screen doesn't happen as often. These are the exact reasons we do a much better job dealing with errors. So the idea, right? The idea is, can we somehow represent human instruction? Add, multiply, subtract, if else, for loop as instruction in binary format, because that's the only thing computer understand. Data will be in binary, right? So what is a good way to represent human knowledge in binary? What's a good example of that? How does string work? Like when you have a data structure, with data type called a string, what does the value 65 mean? All right. Yeah, it's a bit. It's a bunch of bits, right? How many bits? Let's say I look at one character. How many bits are in one character? Please wake up. I know it's the afternoon and I know it's 2 p.m. Perfect time to go sleep and nap. 8 bits, yes. 64 is a little bit too much. For 64, some data, like long integer, use 64 bits. 8 bits. We use 8 bits to represent one character, right? The value of 65 would mean a capital A. 66 means a capital B. 67, a capital C, right? So we can then convert, right, the value of 65 into binary. It would have the length of 8, right? And then when the computer read those 8 bits, it knows that, okay, that means it means an A, right? So then it means that we just convert English as a language into something computer can understand, right? Something from 65, 66, 67, it means ABC. And every single piece of data are binary. Instruction, add, multiply, subtract, these are also binary. How many of you have heard about this terminology called 32-bit processor or 64-bit processor? How many of you have heard about that? All right, awesome. Many you heard about it. What it means is basically yeah. So these are every single processor supports 64 bits. It just means that one word. What is a word? What does a word mean in English? A word. Yeah, something like you can find it in the dictionary. It has meaning, right? It's something that has meaning. So a word in a 64-bit, it means that we would use 64 bits to represent some meaning. Anything that goes into those 64 words will have some meaning. You can map it back similar to how we look up the dictionary and say, okay, what does 1111000011111 mean? The computer version of the dictionary will have that meaning. That dictionary is called Instruction Set Architecture, the ISA, right? So you might have seen that word before in the first lecture when I say what does it mean to be a computer? ISA basically is like a dictionary for a computer. It will go back and know, okay, this means I need to add this number with this number and produce the results. This means that, oh, I'm going to the if else statement. I need to check if this is true, and then I will do this. Otherwise, I'll do the other thing. The 64-bit processor or 32-bit processor just tell me how big is one word. Right? It can be 32 bits, it can be 64 bits. It can be actually that's a lot of depth going into this. We are not going to cover it right now. We'll cover this in the computer architecture class. But just remember, when we refer to a word, think of it like an English word where you can go to the dictionary and you know exactly what it means. So data are in binary, right? If you have 32-bit words, how many different combination of meanings I can have? Assuming one word has one meaning. 2 to the 32. All right, awesome. Basically, this means that we have a dictionary of size 2 to the 32, right? That's quite a lot. That should be enough. That's about a billion, right? A billion, well, actually, it's 2 to the 32 within 4 billion. 4 billion different combination of meanings that we can have. So we can use this to interface, right? Interface between assembly code, which is still look human readable, to a computer. Computer doesn't even understand assembly. We need that dictionary for the computer to understand what is going on, right? So a quick primer about how to represent data. Think of make sure you understand that everything the program do involve data. Every single thing. Input, output, the program itself, everything is about data. And here's how the organization works, right? Each program, each program will have its own view of its own address locations. They own certain amount of land. It owns by a program. This is a concept behind the virtual address, which you'll cover in the next module. I just want to make sure you have this high level understanding that, hey, when I run Google Chrome, right, and Google Chrome has its own internal data, Chrome probably don't want to share this data because many of these data can be your personal information, like a password, right? They don't want to share it with Microsoft Word. It's a totally different program, so there's no point sharing. This is a large piece of land on your memory that the programmer would see, right? They would see, okay, I own this data, and I'm not gonna walk into some random people's data. That's illegal, right? The OS is kind of like the police that make sure that I cannot walk into someone else's land. Right? And when a program is executed, what happened, as I illustrated earlier in the Linux module, a compiler and the runtime basically control this allocation. They tell, okay, this piece of data go here, this piece of data go here in the memory. This piece of data goes here in the memory. They have the full mapping of where the data go. And I mentioned this word, right? And I say is a dictionary of data. So in the computer world, basically, whenever someone said it's a word, one word, it's a unit of data. 64-bit machines use 8 bytes word. Why? How many bytes are in 64 bits? How do you calculate that? So let's say I use n bit, right? How many bytes is this? What do I do? How many? Yeah, basically n divided by 8, right? Make sure you do the math correctly. I've seen so many mistakes on the exam from the previous semester that I feel so bad about it because you did one calculation wrong way in the beginning, and that kind of like has cascading effects where the answer become not obvious. You can get kind of stuck in the middle because of one like small mistakes. Uh, and this is basically a word is a unit, right? It's a unit in which the hardware transfer the data. This is typically done together. Uh, for example, you can actually transfer this whole 64 bits from the memory to the compute unit that do the add, multiply, subtract, do the if else statement. It would operate in this big unit, big data word. And different architecture support different data sizes, right? Some GPU support half word. The A100 that just came out last week support even 22-bit word uh, instead of 32. And then some embedded processor that people use on IoT devices, those word is some of them is eight bits, literally 1 byte instead of 32 bits or 64 bits, or some of them are 16 bits. I want to measure. Let me. Can anyone guess what's the benefit of having smaller words? So my question is why smaller word, right? That's awesome. Less memory for sure, right? Because now my program, instead of storing one instruction would cost me 32 bits or 4 bytes, it would cost me 2 bytes, half the memory constraint. This is a big thing in embedded and IoT. Every single instruction counts. You don't want to write a long program. Why? The DRAM, the memory that goes onto those IoT devices, range from a few megabytes. It can actually even be less than 1 megabyte to something like 500 megabytes. Can you find 500 megabyte DRAM on the market these days? Like, let's say you go to Pantep, right? And then ask the store, like, hey, can I get the 512 megabyte DRAM? They will probably like, we don't sell that a long time ago. It's like these days you're looking at like at least 4 gigabyte, right? And that's a desktop memory. So it matters in the IoT world. You want instruction to be smaller, that saves memory. What else? And this is probably a little bit out of the scope of your whole school, computer science. But I want to make sure you are aware of the more like the engineering aspect of this, right? When I need to transfer a data, what does it mean? It means I consume energy, right? When I need to move one electron from one location to another, that consume energy. Are you all still with me? Basically, every time I have a data going around on your computer, that consume power. If I have 64-bit data, it's going to consume less power than 32 bits. It's going to consume less power than 64 bits. How much less? It's actually more than double. You save a lot of power. And why should I care about power? Yeah. So how many of you have a mobile phone that the battery run out within like 6 hours? Electricity bill, yes, but actually there's actually more common problem than that. Let's look at your mobile phone, right? My iPhone, this is I think iPhone 6, like it's super old. Uh And as you can see, I'm charging it right now. And this is 2 p.m. I woke up at 8. It's only been 6 hours and I need to charge it. Right? So basically usage time of your phone depends on how efficient is the program. Have you ever used some random apps and it's like your phone is actually getting really hot? Smartphone battery run out faster. So let me answer the first question first. Like, have you ever run some app on your phone and you feel like, okay, this app somehow make my phone heat up, like it's hot to the touch. Phone game, yes, that's one of those. Why? It's do a lot of computation. Whenever heat is generated, it means you consume power. That's why the battery goes down really quickly too, right? Uh, Smartphone battery these days, depending on the app you run, sometimes it will make the battery go out sooner. If you look at have you heard of the Nokia like 3110? Like the old Nokia where you can throw it on the one that is like indestructible, the one that go into like every people of my age memes that you can't destroy that phone. That phone battery lasts for like 2 days. Why is that the case? They are stupidly simple. They can do a few things. Call people, maintain the address book, right? And that's it. Yeah, you might have seen it in museum. Yeah, that's a good way to tell how old I am. Yeah, I used it in high school. Uh, so yeah, those phones, even though the battery size is a lot smaller, they are a lot more power efficient compared to these days smartphones, right? And then one of the big design decision if you need to go work on a company that produce mobile phone. Let's say when I was at Nvidia as an intern, one of the big thing that I have to figure out is what is the power consumption of the program, not even the hardware of the program that I need to run. Why is that the case? There's a limit of how much power you can draw from the battery. Which means that if you have 16-bit processor or 32-bit processor, you get the benefit from lower power consumption. Right? So I got super sidetracked here. I hope these are interesting. But at the end of the day, there are trade-off. There are trade-off with almost every single design decision that goes into everything in a computer. Right? And the key here is basically you need to pick the one that has a good trade-off. And the way you access this memory, the way you access the data is done in bytes, right? So basically you will then specify the address, right? The address, as I said in the previous lecture, think of it as this is the entrance to the land you own, right? Uh, this is the exact byte location. Address basically point to that first byte in the word. And then depending on the size of the word, if it's a 32-bit machine, if you move to the next piece of data, it would go by 4 because it's 32 bits, which means it's 4 bytes, right? So the next piece of data would be that address plus 4. If it's a 64-bit machine, that means you go plus 8. In C, if you want to print a pointer, you can use %p. That's a special annotation. It's a %d, which will print decimal, right? You can do %p or %x. %x is a hexadecimal number. These allows you to basically have a much more compact form of the address. And then one more concept that might throw you off if you need to work with IoT and embedded system, right? Because I am sure that some of you might take that class. Bytes in a word can be ordered in a different way. These are called big endian versus little endian. You just need to memorize this. Big endian means that the least significant bytes, right? If you look at the address, the highest address is the least significant bytes. This is used in some computer like a SUN or network protocol. Little Indians mean the least significant bytes is in the lowest address. And you might have been having this question, what do I mean by the least significant bytes? Right? So let's say I store these data in my memory. It's 4 bytes, right? And integer is 4 bytes. Each box is 1 byte, right? And let's say whatever goes into this box is a hexadecimal number FF, or ones, 0F, 0, and then F0. If I want to read this number out, right? If I want to read this number out from a big Endian machine, and let's say this is the highest address, this is the lowest address. What is this number in hexadecimal in a big Endian machine? Anyone want to take a guess?
อาจารย์ both big Indian and little Indian are least significant byte, right?
It's just it tells us where exactly is the significant byte, least significant bytes. Big mean is that had the highest address, right? So if I look at the big Endian machine, where is the highest address? Is it FO or FF? Is it this byte or this byte? Highest address. Yep, F0. Why? I just said this is the highest address. So what is the least significant byte? If I want to get the value of that number, this is what I will write, right? This is the least significant byte, followed by the next least significant bytes. So it will be 0, 0, right? You go from here down to here, down to here, and down to here. So it will then be 0F and then FF. And that's for the big Endian machine. This is the value. So you convert this hexadecimal number into a decimal number, and that's the value. If you look at the little Endian machine, what is the number I'm looking at here? Where is my least significant bytes? Is it FF, right? Is it FFFO? FF, right? So you start with FF. From here, you go here. So that's 0F, right? Then you go here. That's 0, 0. And you go here. That F0. You see that's a two totally different number, right? Completely different number. Depending on whether it's a big Endian or little Endian, you would then get a two different value. So this is a big Endian. So this is a little Endian. And some architecture, like actually processor in the modern day right now support both formats. You can use little Endian, big Endian is also fine. So this is one example. Another example, let's say I assume X is 0x 1, 2, 3, 4, 5, 6, 7, 8, right? And address of X is at 0x10. This is what I would get if I use little Endian was big Endian. The exact same example that I said earlier. So in this case, if it's little Endian, you go from 0x10, which is now at 7, 8, right? And then you go from there, so you get 7, 8, 5, 6, 3, 4, 1, 2. For big Endian, you get 1, 2, 3, 4, 5, 6, 7, 8. All right. So we are done with the concept of word and the concept of big versus little endian. Let's actually look at data type, right? And let's start simple. Let's look at the character, the 8-bit representation in ASCII, right? In ASCII that everyone have heard and like, that's how we represent character. So what is the log2 of 256? Unicode, basically, Unicode is another representation that requires more bits. It has a table that say, okay, this value map to what? It's a, think of it this way, it is another set of dictionary to translate binary value to letters. Yes, that's actually one good way to figure out what's the log of 256. You go from 1 to 2 to 4 to 8 to 16, basically every time you multiply by 2 and see how many times you have to multiply by 2 until you get 256. And the reason why I asked you what's the log 2 of 256 is when you are doing an exam, it will get more and more common for this class to convert binary value to decimal and decimal back to binary value. So let me give you some recap on a binary number. What is the value of, okay, I'm just going to throw in a conversion from binary to hex, right? A hex number. So let's say I write in some random number in binary. All right. I don't even know how many bits is this. How would I convert this to a hex number? Anyone know a good trick? Group
Separate by 4.
Exactly. Break it into 4. Why do we need to, why is it a good idea to break this into 4? So you break this by 4 things. But to make sure that everyone understand the logic behind this process, I want to make sure everyone understand why is it a good idea to break this into 4. How many values can I get from a 4-bit binary value? Exactly. 4 bits means one hex number, basically one letter in the hexadecimal representation, right? So if I group this by 4, I get one digit out of the hex number. What is 1101? 1111 is an F. What is 1101? That's 1110. Basically, if you know that 1111 is an F, you start from there and you subtract 1 every single step, right? And then when you subtract 1 from F, you then get 1110. That's an E. You subtract 1 again, it's 1101. That's a D. So this is an E, as I said earlier, 1110 is an E. What is 1011? That's 8 plus 3, 11, right? What is 11 in hexadecimal? 10 is A, 11 would be a B, right? This is 7, right? 0, 1, 1, 1 is 7. 1, 1, 1, 0 again is E. 1, 0, 1, 0 was that, is 10, right? So that's an A, and that's 1. So this number is converted to 0x, 1A, E, 7B, ED. Right? So this is useful when you have an address and you want to figure out what's my binary value of this address. Another good trick is if you have a decimal number and you need to figure out how many bits is used to represent that. Right? So you use a lock for that. Basically, the conversion is this. You have the ceiling lock to of n. Basically means that how many bits are needed to represent n, right? And one good trick that I usually do is, what is 2 to the 10? If you do the math, that's 1024. That's roughly 1000, right? 1024, 1000 off by 24, who cares? If they want to approximate things. Which means, what is 1000 square? 1 million, right? 1000 square is 1 million, which means that if I want to approximate 2 to the 10 all square, which is 2 to the 20, that's around 1 million. Right. So every time you need to add three zeros to the number, that's kind of like you multiply this by 2 to the 10. Which means that you can basically break the number into, is it within 1000? Is it between 1000 and 1 million? Is it between 1 million and a billion? No, a trillion. 10 to the 9. Then is it between 10 to the 9 and 10 to the 12? Because every time you increment by 10 to the 3, multiplicatively, basically, then you add 2 to the 10, you multiply 2 to the 10 to that, right? So it would then help you trying to figure out, okay, how many bits do I need for this number? This will come in handy when we go through the fourth module. And I'll be honest with you, on the exam, I'll give you a conversion table, but it's good to have and good to make sure you can kind of like come up with the log version, log 2 on the fly, using these tricks. All right, so let's go back to our material. Now that we have a recap on how to convert binary to hexadecimal and also decimal to binary. Right? What is a string? As I said, it's an array of character, right? So this is encoded in ASCII and a null value, as I said. Yes, it's character array. This is the end of string. So if I want to say file pro, which is the old name of this class, I would then have an array of string that have FILEPRO, right? And then the value 0 at the end. Any questions about the string? That's it for how do we represent string in C. And actually this is true in many programming languages. How about an integer? Same question I have earlier. How do I convert a decimal number into a binary value? Right? That's how you represent an integer. In NCC, which is the old version of C, a short integer is the same as integer, which is 2 bytes. Right? This is between the negative 32,768 to positive 32,768. In modern day, integer is 4 bytes. These depend on the version of C as a programming language that you are using. And that's why it's always safe to use this function size of to check, okay, what's the size of my integer? Because that change over time, that change over the language, right? So to be safe when you do malloc, don't just put in a flat number. You do size of data type multiplied by the number of items you want to have. What is signed versus unsigned? How many of you heard about that? Basically, signed and unsigned means that whether I want to be able to represent a negative number or not, right? Integer can, for example, be positive and negative number. When I say unsigned, means that there's no negative number. It's start from 0, go to whatever value, whatever how many bits do I have for that integer. Sign, we would then use the two's complement format. The way you can calculate two's, it exactly is like a two's complement. Anyone have not heard about two's complement so that I'll go over what it means? That's actually what it means. Basically, if you have let's stick with 1 byte integer, right? Actually, I'll do 2 bytes. The NCC integer 0 1 1 1 0 0 0 1 1 1 0 0 0 0. What is the value of this? This is the most significant bit, right? And this is the least significant bit. And as I said, the most significant bits here is just the sign, whether it's a positive or negative, right? So what do we do for this calculation is we look at this, right? And what's that value? It's a 0. So you will say 0 times 2 to the and that's a negative value. So it's 2 to the 15, right? Because there are two bytes plus the decimal value of this. Right? This is 2 to the 0. This is 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. What's 2 to the 4? That's 16, right? This is 32. This is 64. This is 128. That's 256, 512, 1024, 2048, 4096, 8,192, and this is 16384. If I do it correctly, basically you then add every single number up, replace this with the results, and then you get the value. What would happen if the most significant bit become ones? It means that then this becomes a 1. Then the actual value will be negative. Right? And for a constant, right? In C, you can force a constant number to be unsigned by typing in the capital letter U at the end of the number. So if you write in 15U, it means that I'm going to have the number 15. Interpret that as an unsigned value. All right. Why is this important? This is what happens when you mix the two numbers together. If you have both signed and unsigned, the signed value will be converted to unsigned, and you add the two numbers together, becomes unsigned. So it's a lot safer to convert your data type to make sure in the equation they are the same data type. Otherwise, you're gonna have fun debugging. In most cases, program would likely to behave correctly, but sometimes you might run into bugs because of these exact reasons. Another reason you can run into bugs is extension and truncation. When you have a negative number and you want to cast, say, from integer to long integer, which is 2 bytes into 4 bytes, right? What is happening is, let's say you have this as an integer. How many bytes is that? So this is a negative number in long integer. I mean, in an integer, that's 2 bytes of data, right? So what if you want to convert into long int? What we need to do is to keep everything here the same. So we have 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1. Then you just add all the ones until the end of the data size. Why does this work? Basically, when you extend all the ones here, it doesn't actually change the numerical value. If you do the conversion, regardless of the data size, you get the same exact value because it's as if you multiply the negative side by 2, multiply, then add 2 to that new bit that just added in. So you get the exact same value. That's why to choose complement format is a good thing. It's easy if you want to convert one data size to another. Truncation, when you want to say cut from 4 bytes integer to 2 bytes, the value will change. The value will change for both positive and negative if you cut and you get rid of some of the ones. It would just basically drop the n most significant bits. So let's say you have this value, right? So that's 1 byte. That's the second byte, right? You want to convert it to a 1 byte data. This is all gone. This is the value you get, right? Regardless of whether it's assigned or unsigned, it's a totally different value. So when you do the conversion, make sure that you're aware that if you do extension, you get the expected results. But if you truncate, that value can change. Any questions about integer and truncation extension before we go into a floating point number? All right, so let me actually, so that's a question that actually is the legit like confusion question. Why when I do this extension, why does the value stay the same? Right. So let me just look at these number, right? And let's say I extend it by just one single bit. What happened? Right. So basically extend it by one single bit, I add 1 to that, right? So it's 1 0 1 1. Right. And then I add this one more bit. The equation to get the value is this, so the actual value equal what? Most significant bits times what? 2 to the bit location, right? And that's the negative side plus everything else, right? When you extend, which means that you add this one more bit, right? This extra ones here. And let's say this is 2 to the n. What you're doing here is you do negative 2 to the n plus 1, but this become a positive, right? So plus 2 to the n plus everything else here, right? What is this? What will I get when I do negative 2 to the n minus plus 1 plus 2 to the n? Is actually equal to negative 2 to the n, right? Basically, when you extend by just one extra bit, this is the same as you do negative 2 to the n plus 1 plus 2 to the n. That results in negative 2 to the n. Right? So this box here is equal to this. If you don't trust me, you can do this. Let's say n is 5, right? 2 to the n is then 32, right? So if n is 5, 2 to the 6 is 64, right? Then you get 32 because it's 64, negative 64 plus 32, which is the same exact thing as this equation, negative 2 to the n plus the rest. Right? That's why when you do extension, regardless of what you add, if you just add 1 and 1, the value stays the same. Because the ones that you just added get canceled out, which means that you ended up with the same equation, which means that you ended up with the same exact value. All right. And this is the key. Basically, this part is the key. When you add just by one bit, you get the same equation, which means that you can prove that no matter how many bits you add, it will be the same equation as well. All right. So floating point number, basically they consist of three things. Signed bits. The most significant bit is either 0 or 1. 1 means that's a negative number. 0 means that that's a positive number. Those are the simple part, right? There are two more pieces of information. The bits that we call exponent bit and the bits that call mantissa bits. And I'll show you the example. But this is the equation. The exponent bit goes into this part of the equation. You multiply everything by 2 something, depending on the value that goes into this exponent bits. The mantissa bits, think of it as this. It's 1 plus, right? 1 plus, and let's assume mantissa bits is like 5 bits long and it's something like this, 1 0 1 1 1. This would be convert to something like this. The most significant bits of my mantissa bits is 1. So that's 1 multiplied by 1/2 plus 0, right? Because the second bit is 0. 0 multiplied by 1/4 plus 1, right? Now this the third bit. So that's 1 multiplied by 1/8 plus, that's the fourth bit. So that's 1 multiplied by 1/16 plus, again, 1 multiplied by 1/32, right? So that's for a 5 bits long mantissa. In the typical floating point, the mantissa is 23 bits long. There are 8 bits exponent, 33 bits mantissa. This determines the value of floating point number. So let's do one example, right? let's say my floating point number is this. Sign bit is 0. My 8 bits exponent bit is 0, 0, 0, 0, 1, 1, 1, 1. Okay, that's way more than 8 bits. 0, 0, 0, 0, 1, 1, 1, 1. Right, so that's my exponent bit. And this is the mantissa bit. And for simplicity, it's 1 and a bunch of 0. And then end with one more 1, because I don't want to write a long equation. What is the value of this floating point number? So you know it's a positive number, right? Because the sign bit is 0. Then you have 1 multiplied by 2. What is the value of 0, 0, 0, 0, 1, 1, 1, 1? That's 15, right? So this is basically 15 minus 127 multiply, right? Multiply by, what is my representation of all this mantissa value? As I said, you start with a 1, right? Plus, you have a 1 here, so that's 1 multiplied by 1/2, right? And then everything else here is 0, and you have 1 more 1, so that's 1 multiplied by 2 to the negative 23, 3. So because there are 23 bits, the last bit is going to be 2 to the negative 23, right? This is the actual value of this number. Any questions? Basically, that's 2 to the negative 112 multiplied by 1 plus 1/2 plus 2 to the 23. Any questions about how to convert a floating point number in a bit representation to an actual value? Basically, the key here is you use the exponent bit literally as an exponent to 2 to the something. And then the mantissa bit goes into what is the base that I need to multiply 2 to this something with. Right? So the cheat sheet or the solution is follow this equation and you get the value. All right. Any question before we switch to the next topic, which is Boolean algebra? Now that we know how we represent data in an integer, in a floating point, character, string, just keep in mind that every time you deal with data, these are the bits that go into the DRAM, go into your main memory, and that's what get read out when you run the program. All right, so let's go through a Boolean algebra. The content of Boolean algebra would heavily go into your assignment 3. Basically, here are the basic. How many of you take some basic logic class before? Like, what is A and B? What is A or B? What is if A then B? Basically, this is every single value in Boolean algebra is either 0 or 1. 0 means false, 1 means true, right? And there's another concept called truth table, which kind of represent all possible results of my Boolean algebra. And here are some example of the operations, right? Instead of add, subtract, multiply, then you have and, or, not, XOR, NAN, NOR. NAN is basically not and, NOR is not or. So if A is 0, what is not A? 1. Basically, you flip from 0 to 1. What about A and B? This hat means and A is 0, B is 1. 0. All right, awesome. I know it's getting boring. Maybe a lot of you have heard about this. Just want to make sure. How about or if A and B, if A is 0, B is 1? That's the one. You got it. Basically, then if you add not, if you add or, if you add all these things, then you get a different binary value. Why are they important? There's a theory behind the fact that if you can build a circuit that can either do NAND or NOR, just one of them, you can build every single operation in the world. You can add, you can subtract, you can multiply, you can do if else, you can build a computer. That's the key. If you can do a NAND gate or a NOR gate, you got a computer. And actually, that's go behind whatever is running on your computer right now. Like that is built from either a NAND gate or a NOR gate. That's probably like the most basic elements that go into your computer. So the reason why Boolean algebra is important for performance of your program, it kind of hinting that, hey, if I know that I need to do A plus B plus C plus something, I can always convert back to and or, and sometimes you save a lot of operations, and you see that in assignment 3. There are some tasks that can convert complex operation into one logical operation, and you got the results. You can actually speed up your program. In fact, when you compile the program, this is done on your program to make sure your program runs faster by the compiler. The GCC, when you type in GCC, they look at your code and they actually try to optimize it and say, okay, what else I can do when you do, let's say if you do 5 times 4, you can actually convert this to a shift operation. This is actually 5 left shifted by 2. A multiply operation is a lot more complex than shifting. In one conversion, you get the exact same results, but a lot faster. How much faster? About 7 times faster right now. If when you just do this conversion, the program would run, just that one line would run about 7 times faster. So hopefully this convinces you that if you know some basic Boolean algebra, sometimes you can optimize your code, make it less human readable, but faster. So think of it this way, bits, right? Bits of your data are grouped in a vector where let's say your data is 15, right? Your data is 15 and this is a 2-byte integer. This is essentially what your data would look like, a bunch of 0 followed by 4 ones. This is a vector of binary value, a vector of 0, 0, 0, 0, and 1s. What's the first element of this vector? 0, followed by more 0, followed by 2 more zeros, and followed by 4 ones. Operations on Boolean algebra is done on this bit vector. So let's say I want to AND, right? Do AND. It's the 1, 1, 1, 1, 1, 0, 0, 0. What will I get if I do this 15 and this number? You would do this and that's a 0, that's a 0, that's a 0, that's 0. 1 and 1, that's a 1, right? And then this 3 is a 0. So 15 and what is this number? That's, oh, that's 8, right? 8 plus 16 plus 32 is 64, 128. That's 192. And then plus 32 plus 16, right? So that's 40. That's 56. So 192 plus 56. That's 8, 4, 248. Basically 248 and 15. 248 and 15, which results in 2 to the 3. That's 8. Why? Because you do bitwise and. Any questions about how Boolean algebra work in C and D? These are the operations. Basically, if you do 248 and 15, you get 8. If you do 248 and 16, what will you get? Wait, why 9? What is 16? 16 is basically 1, 0, 0, 0, 0, but ones and then 4 more zeros, right? This becomes a 1, the rest becomes 0. If you do this and, you'll get 16, right? And or what is 248? And or is this vertical line, right? 248 or 15, what will you get? You can type in binary too if you don't want to convert it back to decimal. Yeah, all ones, right? Because you do an or for all of this, that's 255. What is not 248? Not 248. Basically, I would then, this is 248, right? I would flip everything. So that's 0, 0, 0, 0, 0, 1, 1, 1. This is equal to 7. Yep. Left shift and right shift. Okay. This hat is XOR. What is 0 XOR 0? 0 XOR 0 is a 0. Basically, if it's the same number, it's a 0. If it's a different number, it's a 1. That's why it's named exclusive OR. What is an OR? An OR means that I need at least one of the ones to make it a 1. Exclusive means that I need the exact one of the ones. If it's both ones, I don't care. That's why it's, if that's one of the ones, we get 1. All right, so that's an exclusive OR. So what if, let me erase some of these notes because there's more thing coming up on the slide. What if I do 248? Just want to make sure I don't write on the next text that are going to show up. Exclusive or 15. And you can answer in binary, that's fine. This will equal what? 1, 1, 1, 1, right? No, I don't want to exit. Equal 1. Oh, I can't. So, okay. This is 11110111. That's 250, 248 exclusive or 15. Make note that this is different than the logical operator. The logical operator is this. This is not. This is and. This is or. The thing that go into the if-else statement, they would treat it as if x is true and y is true. It doesn't do this bitwise operation. So one of the trick that I usually do is to use this as a set operation, right? Let's say I represent 1 means that the number is in the set. 0 means that the number is not in the set. Let's say I have the number that can go between 0 to 55, right? In my set, I can have any number from 0 to 255. I can then have a bit value that consists of 255 different numbers. So this is 255 bits, 256 bits. Right? There are 256 numbers, 0 to 255. If the first number is 1, it means that 0 is my set. If the sixth number is there, it means that my set also has a 5. If the other last number is 1, it means that I also have 255 in my set. So that's my set that consists of 3 numbers, 0, 5, 255. If I have another set, how do I perform intersection? Everyone here knows the definition of how you can intersect two sets, right? Set A and set B. If it's a set of number, how do I perform intersection on this set? And then let's say I have another set that has 0, 10, and 254. This is set B. So A intersect B would equal 0, right? But how will I get that easily? Exactly, you can use an AND. Because everything here is a bit vector, right? I perform an AND. When I do an AND on this two set, the only number that becomes 1 is the first bit. So then I'll know that, okay, this is a set that only have the number 0. If I want to do a union, I can do an OR. If I want to do a symmetric difference, I can use XOR. A complement, I can use the NOT, right? So I have one more question. Let's say I have an array. Let's say I have an array of a pair of numbers, something like this. 1, 1, 5, 4, 5, 7, 4, 10, 7. Right. So this is my array. And notice that there's only one number that doesn't have a pair. There's 10 doesn't have a pair. The rest, that's 2 1s, 2 5, 2 4s, 2 7. How can I tell? Is there a way I can tell that, hey, that's number 10 that doesn't have a pair? If my array have one number that doesn't have its own pair, are there any tricks I can do to actually find out that number? Yeah, you can use exclusive OR. That's awesome. Yeah. So if you do exclusive OR on every single number here, if you do 1 XO1, XO5, XO4, XO5, XO7, XO4, XO10, XO7, you will get 10. Right? This is a lot faster than writing a bigger program to loop to all the elements, keep track of how many numbers appear how many times. You XOR everything, then you get the number. Interestingly, there was one of the random interview question that I had like when I was an undergrad, trying to get an internship. And I kind of find it interesting that you can do like these bit operations to to do tricks to make program faster. So let me kind of cover the last few things for today. There's also this concepts between logical shift and arithmetic shift. Logical shift is just literally shifting. I don't care about the value. I just look at the raw bit vector and I shift it. Arithmetic shift would preserve the most significant bits. What do you mean by that? Let's say I have a 1101, 1110. This is the most significant bits, right? And in a signed integer, that's a negative. It tells that here, this is a negative value. This is a negative value. If I do logical shift right by 2, I would get 11101100, right? You add one more 0 and you take off the 2 bits here. This is logical shift. But if you refer to arithmetic shift, when someone say, hey, do an arithmetic shift, 11011110 shifted by 2 would equal, you preserve these 2 bits. That becomes a 1, then 110111. What is the benefit here? The benefit here is if it's a signed integer. A signed integer, when you do a shift, that's an arithmetic shift, the number remain negative. That would preserve the negative, basically the fact that the number is negative. And one trick is when you do right shift, one right shift is divide by 2. If you do 2 right shift, divide by 2, 2 to the 2, which is 4. Basically, n shift by m is basically would then mean n divided by 2 to the m. If you do left shift and left shift by k, this is n multiplied by 2 to the k. And that's how you can change the multiply into something that's a lot faster. When shifting, you get the results. Let me stop here and do a Q&A because it's already been 1 hour, 1 hour and a half of me talking in monologue. And I think a lot of you probably is napping right now or like dozing off. It's a lot of material that is not that, some of these are not that exciting. It's just me telling you, okay, this is how you do it and this is how you do it. Or feel free to check out the video. As I said, I hope it's there. And then I'm going to do right now a Q&A. If you are going to in-class exercise from Monday, you can ask the question now. Next Monday, we'll have another in-class exercise that deals with the topic we cover here, including what's coming next. Feel free to check assignment 2. Feel free to ask me questions about assignment 1. In the meantime, I'm gonna go through your email. I'm so sorry about that as well. I'm gonna go through your questions for assignment 1 that you've been asking since Monday. All right, so I am going to save all the annotation here and switch back to my desktop so that I can do a Q&A a little bit better. Feel free to just type on the chat. Feel free to also just ask me loudly. And one thing I want to make sure you are aware is like one of you kind of contact me about the interest of like, hey, what should I do if I want an internship during the summer? And then one thing